Hello, everybody, and apologies for the short delay. So we are very happy today to have our speaker, Yorgos Chintzoglou, who is a senior research scientist from Lockheed Martin Solar and Astrophysics Lab at Palo Alto, California. So a few words about Yorgos. Yorgos received his degree in physics in 2009 from the Department of Physics of the Ioannina University. Then he obtained his PhD in 2016 from George Mason University. Then he worked from 2016 to 2019 as a postdoctoral scientist in University Corporation for Atmospheric Research, mostly known as UCAR and Boulder. And then at the same place from 2019 to 2021, he assumed the role of Project Scientist 1. From summer 2021, Yorgos is a senior research scientist at Lockheed Martin Solar and Astrophysics Lab. Yorgos is a worldwide expert in the analysis, modeling, and interpretation of solar magnetic fields, EUV images and spectra, atmospheric heating and structuring and dynamical phenomena such as flares and CMEs. He is heavily involved in the development, calibration, operation, and data analysis of various current and upcoming solar physics, spaceborne, and suborbital instrumentation, including AIA, IRIS, EUVST on Solar Sea mission, Herschel, and VOLT. So he has a very unique skill set, not only being an expert in data analysis and modeling, but also in instrument development and calibration, which is kind of very unique. Today's seminar will be about a very recently approved solar physics mission called Muse. So Muse will bring solar spectroscopy into a completely new era. So now, please, Yorgos, the floor is yours.
Thank you so much, Spiro, for the very wonderful introduction. And thank you so much again to you and to the president of the Hellenic Astronomical Society for the very, very nice gesture to invite me to give this talk. Let's get to it. Okay, in 1664, Isaac Newton attended a fair in the very place he used to live at that time, which was Cambridge, England. During this fair, he bought a pair of prisms and he went home. And then the rest is history, really. For example, we all know the experiments that he carried with this pair of prisms. Here is a depiction of those prisms in an old book of the previous century. Newton is also known for being the first who actually used the term spectrum to denote the succession of colors in terms of wavelength called red, orange, yellow, green, blue, indigo, and violet. Then we have quite some time after Wollaston, another famous English physicist, who actually had the idea to add a slit. He used one prism and one slit. Basically, he covered his window with an opaque material. He cut a slit so that he can allow a line like a linear like opening to allow, to permit light to go through, and in a dark window, in a dark room. And as the slit light passed through a prism, he managed to see a certain succession of dark shadings in the spectrum of the solar light. He didn't know what it was, but he did observe, he did report it. Then about a decade later, Fraunhofer, Joseph von Fraunhofer, discovers exactly the same thing independently, same thing as Wollaston. And after that, the rest is history. It's the so-called Fraunhofer spectrum. Here you see a design, which is pretty much a lithography prepared by Fraunhofer himself, and it has been replicated multiple times in the literature since then. And you see the succession in German color. Fraunhofer was actually Austrian, And you see with German words the different colors, pretty much the same number of colors as Newton defined. And on the top, you see the characteristic black body spectrum, even though people didn't know what it was, which is actually how the peak of the solar radiation is recorded to be on the top plot. And on the bottom, you see the succession of those dark and bright stripes along the solar spectrum. He also showed that these dark lines were not due to his prism by rotating the prism around, and were not due to the Earth's atmosphere by doing exactly the same experiment different times in the day. So the lines were exactly the same location. He did not have an understanding of what these lines were. Fraunhofer, he also started playing with diffraction gratings, which is a different dispersing element. And he was able to study the so-called spectra. So he came up with the word spectra instead of spectrum, because using a dispersing element, you actually see multiple versions of the spectrum because of the way of the order of diffraction. So he is also the first one that we know that he understood that, and he actually used different dispersing elements to study the spectrum of the sun. And then we have Kirkham and Bunsen. They were the people who founded spectroscopy as a science, the people who developed the spectroscope as an instrument, where they either used prisms or diffraction grating, actually. And with them, in 1859, we have the era of sophisticated instruments for solar astrophysics to begin. Here's a spectroscope. It is basically composed of a dispersive element, a collimator with a slit, and a small viewing telescope, which is different than the actual telescope that is used to provide the light to the slit. This is not shown here, as you see on the top left. Bunsen and Kirchhoff performed a series of experiments by heating different kinds of material and gases, and found that different elements had their own unique spectrum, their own signature, so to speak. Spectroscopy was born because of that. It didn't take too long when a spectroscope was pointed at the sun, and early observers, such as the legendary Norman Lockheed, a legendary British solar physicist, began identifying the mysterious Fraunhofer lines with known elements found at the Earth. At the same time, the same person, Lockheed, detected spectral signatures just above the solar limb, the edge essentially of the sun's disk. And you see this, I don't know if you can see my mouse pointer, probably not. Okay, here it is. This is the solar limb. This is in other words, the edge of the sun. People were not really able to see anything around it. Typically, only in solar eclipses, people would see when the sun's disk was obstructed, some red flame-like structures, like red fires that used to be called. And they didn't really know what it was. And then Lockheed managed to use a spectroscope without really seeing the flames, because the sun was not obstructed normally by the sun. He was able to determine that there was some conspicuous structures that gave birth to a spectrum, even without being visible. So that was because of Norman Lockheed's genius, really. Still, the spectroscope is using a single dispersive element at that time. And then the question is, can we do better than essentially what Fraunhofer has done or Wollaston have done? All of them used just one spectroscope and a slit. So that's really the question, and the answer is yes. Some early observers figured out that if you can use prisms in series, and that's definitely not a problem because of the bright light source of the sun. So it's possible to actually use them in the setup that you see in this image. By doing so, why this was really a big deal was because using multiple prisms in series or dispersive elements in series increases the dispersive power, which allows to stretch the spectrum and essentially isolate more and more the spectral lines, have them become more and more resolved. And then even lines that are very thin or faint to be seen as individual lines can actually appear much clearer. And this is the kind of instrument that Lockheed and other contemporaries in the mid-1800s, after the invention of the spectroscope, used to prove that the solar atmosphere is the shell of glowing hot gas around the sun. And also discovered the element helium, coincidentally, 3 decades before it was even discovered in lab experiments on Earth at the end of the 1800s. So groundbreaking discoveries with groundbreaking solar instrumentation. But then someone, somewhere, thought again somewhat differently. As we said, using a so-called train of prisms or using prisms in series allows to stretch the solar spectrum more and more, essentially select a particular region and expand it, stretch it, and basically be able to study in more details very strong spectral lines. Thanks to that, another observer called Huygens in 1869, well, 10 years from the first invention of the initiation of the spectroscope as an instrument, he actually increased the width of his spectroscope's slit, and that's what you see here. This is basically just an image of the sun projected on a slab of metal, and here is basically a screw that by turning the screw in and out, one can essentially increase the width of the slit. And in this black region, this is where light from the sun at the edge of the sun can actually pass through. And this is how things may appear. So when he opened up the slit using a high dispersion in the way that I mentioned with multiple slits, he was able to see an image form within the spectrum. So in particular locations where you have a very strong spectral line. In this case, it's the H alpha line or the calcium line that was also a big favorite. So, and you can see multiple observers actually drawing all kinds of different things that they were routinely seen every single day, and even without waiting for eclipses. You didn't just measure the spectrum, but you could actually make, in some ways, spectrally clear images, spectrally pure, not in the very sense spectrally pure, but in the sense of making images that are in one axis you have the wavelength, but then if you have a strong dispersion, then the wavelength is not necessarily confused that much. However, that only worked in the edge of the sun, in the so-called solar limb. When people try to measure, to take such images on the disk of the sun, that didn't work because the sun is exceedingly bright. The photosphere of the sun is excessively brilliant. So that wasn't the case until another novel instrumentation brought a huge leap forward. And here you see what is now known as the Spectro Heliograph, which was developed independently by George L. Hel and Henri Delandre in the late 1890s. By combining photography with spectroscopy, it was possible to produce spectrally pure scans instead of the wide slit views that I showed in the previous slide, that only work above the solar limb. And this was possible by making the slit very thin. So obviously you cannot really make an image right away, but scan it, move it from left to right, if you like, as I show in this illustration, along the solar disk, and covering both the limb and also the surface. So depending on the location that one is tuning it along the wavelength, is able to scan features whether they're on the limb, on the disk, and also on the solar limb. So in some ways, very similar to what we had in the original spectroscope, only that we are moving the location of the slit along the plane of the sky and recording at the different slit position and forming an image, if so to speak, as along the scanning direction. This same technology is used today, 130 years after. For example, we have Hinode eyes, which has an EUV. It works in the extreme ultraviolet light and makes such spectrally pure images and spectra. Iris, which is a much faster instrument than ICE because it's more new, better technology, but it's focusing on a different wavelength range and different physical region on the sun, which is a chromosphere and the transition region. And very soon we'll have a UVST, another classical spectroheliograph or spectrograph, which will allow us to form such images. And that will be, I'm also working on the development of this mission, in particular the slit jaw imager, which is basically making quickly spectrally isolated images of the sun. So the challenge is that, first of all, we have many problems in solar physics that remain unanswered. This is because producing scans of extended solar regions and thus spectrally pure imaging and invaluable diagnostics, such as Doppler velocities and thermal width, cannot happen instantaneously. Scanning from left to right, as you see in those images here, takes time. It may take more than a few minutes to hours, depending on the spatial or spectral resolution and the signal strength of the features we want to observe, which may require long exposure times. All these limitations render such a powerful instrument, in one hand, the Spectro Heliograph, inadequate in helping us make more progress on big open problems in solar physics, including the physics of solar eruptions, which develop in timescales of order of a few seconds. So it is about time for a new breakthrough in instrumentation. Introducing the multi-slit Solar Explorer, a mission using revolutionary imaging spectroscopy for breakthrough science of space weather and the sun's corona. Muse is a mission which aims to determine which mechanisms heat the solar corona and drive the solar wind. This is also designed to help us understand the origin and the evolution of the unstable solar atmosphere, essentially the solar eruptions. And last, it will allow us to investigate fundamental physical plasma processes in a way that has not been possible in the past. Of course, nothing is really easy, not for any level of sophistication of any solar instrument. There are several problems and challenges. Here I will atomize a few of them. The first problem is that imaging instruments, for example, the already accessible and available ones that are in orbit, for example, the atmospheric imaging assembly that Spiro mentioned earlier, or the extreme ultraviolet imager, which is actually on the solar orbiter mission and currently taking images. And the Hel.A.S, which is a suborbital mission, flew from Marshall, developed by Marshall Space Flight Center. All of them provide limited diagnostics. All of these that I just mentioned. They are imaging instruments, bandpass instruments, and they do not have spectral information, so to speak. There are some workarounds that one can extract such information, but we do not have the diagnostics that we need, for example, the Doppler velocities or the width. So that's a problem we are living with, while we have such instruments with sub-arc-second resolution, which drive our progress forward. But again, imagine how much progress we could do if we had the spectral information unavailable. The second problem is that single-slit spectroscopic instruments, as I mentioned earlier, Hel.A.S, IRIS, EUVST, and also SPICE, currently on the solar orbiter, miss the big picture. Why? Because I said scanning from left to right of any arbitrary region on the solar atmosphere, whether on the disk or on the limb, takes time. And you have to go back like a typewriter. For those that have used them in their, they know that, you type from left to right and then you have to go back. It's like exactly how it works if you want to actually cover the spectral and temporal information, in a continuous kind of fashion. So you miss the big picture because there are phenomena that evolve in timescales much faster than we can capture with the scanning time available. Even though the sun is a very broad structure, you still need a lot of exposure time because those instruments are operating in the extreme ultraviolet light, not in the visible light. But that's where the new physics are discovered mostly. Because white light instruments are still great, but from space we can actually do much better understanding in shorter wavelengths as well. So that is inaccessible from the ground. So there's a lot of discovery space there. And the last one is the low resolution and low cadence that I just mentioned of the coronal observations, which miss the fine scale structure and intermittency of the effects. So let's take one by one. Why do we need sub-arc-second spectroscopy? Is the obvious question, a question that NASA would have asked us and asked us to convince them that we have the grounds to propose such a mission and be selectable. Well, we have Hel.A.S, as I mentioned, which was a suborbital experiment, or we have Hel.A, which is an orbital experiment, and Solar Orbiter, EUI, which have revealed the importance of small scales, sub-arc-second structure, essentially, on the sun. 1 arc-second as observed on the plane of the sky corresponds to about 720 kilometers on the surface of the sun in linear scales. It's an angular distance, but you get this kind of equivalence, at least the center of the solar disk. So you get an idea. So we're talking about these obvious structures even less than that. That's what we mean by sub-arc-second. So, and not just that there are small features, small structures that can be normally under-resolved by the already existing instruments, but there is an intermittency in the way the coronal environment develops. For example, the formation of current sheets that are driving reconnection, dissipate and the dissipate of their currents in heating local plasma, the occurrence of three-dimensional magnetic reconnection, which can also be under-resolved because it happens at small scales, and also understanding MHD and instabilities in such small scales. So we need better instruments to go to smaller scales. Now, the other thing is this, and I will have this movie play, which is a very dramatic movie, one of the first movies that were achieved by the IRIS mission during its first year of operations. This shows a transition region and shows an abundance of subarachnoid structure and dynamics. You see what I called earlier, you heard me talking about it again and again and again, the so-called solar limb, which is the physical edge of the sun, which obviously extends more in different wavelengths because we see different portions of the atmosphere. Higher up, we see a multitude of suspended structures, which are basically prominences or coronal rail. And this is actually an explosion, so to speak, a magnetic explosion that you see it juts upwards and along the radial direction, plasma, hot plasma on the sun. And we see it in this far ultraviolet image sequence of images. Here you see not images produced by a spectroscope, but images produced directly by a reflective instrument that is actually a passband. It's a so-called slit jaw imager. What you also see is the spectral slit, the slit of the spectrograph. And it is using this slit that goes from left to right and forms a short raster that we call, what gives us the spectral information. And as you see, I play the movie again. If you are able to form an image only with spectral information only with this region, you're missing all this information around the field of view. It's just impossible. There is no way you can do it. And given the timescales you just saw. So the cadence of this movie is a few seconds per frame. So you get the picture, hopefully now, of why this is important to go beyond the norm, go beyond the single slit raster or single slit instruments to keep up with the dynamical evolution, and also develop diagnostics at the same rapidity required. And here's a schematic of our mission, the multi-slit solar explorer. It's composed of two instruments, basically two telescopes mounted in very similar ways on top of this electronics box, and we have the solar panels, as you see here, the aperture. For the spectrograph, we use 25 centimeters telescope, and for there is a second telescope called the imaging telescope, which is actually providing bandpass images at very high resolution. And both of them are observing simultaneously. There is a guide telescope that tries to correct for the inconsistencies of the pointing to the sun. So that's another thing that you need to have in space. It will be launched in 2026. NASA approved us for this early launch, which is great news because this is closer to the middle of the solar cycle, so to speak, close to the so-called maximum. 2028 will have meant that we'll be losing at least 2 years of additional solar activity going towards the solar minimum. And that will allow us to get more statistics and actually do our hypothesis test of the different solar phenomena. It will fly in a sun-synchronous polar orbit, which is about 600 kilometers above from the surface of the Earth. And that will allow continuous observations with only a small interruption from the so-called eclipse seasons, when the orientation of basically the way the spacecraft is revolving around the Earth in such orbit undergoes short eclipses for a fraction of its period for 2 parts of the calendar year. So, but that's a necessary evil. We maximize observation for about 7 months in an uninterrupted fashion. The mission nominal period is 2 years. As it's often the case, you have to define 2 years, but so was the case with other missions. For example, IRIS was about 1 year, 1 year and a half, or other missions, for example, AIA, it was close to 5 years, and then you have the extended mission. So within the 2 years, we promise that we'll be able to solve all those big problems, obviously, shooting for the stars, as we say, but we're very confident that will be the case. There is a lot of flight heritage, meaning that all this technology you see to some extent has been tested in space, except for obviously the multi-slit array, what makes this instrument new. But we also have the technology demonstration and readiness available for all those aspects and components in various ways. That's pretty much the schematic. I maybe talk too much about it, but just giving you another perspective of our instrument. Now you see a top-down view of the primary mirrors for the spectrograph and also for the context imager. So you see they are actually coated in sectors to enable reflectivity in different spectral bands. That's the way we optimize the instrument's function. Using not just one slit though, but an array of 37 slits simultaneously, the Muse spectrograph will be capable of obtaining spectra, spectrally pure imaging, and other important diagnostics of the plasma, as well as of flaring and eruptive events in the solar atmosphere over a very large field of view, and at a rate that is 2 orders of magnitude faster than the already existing instruments in space and on the ground. Muse's context imaging will be of the highest resolution in space and time ever achieved, which is about 10 times better than the current instruments, to better enable the study of the dynamics and the nature of the solar transition region and the corona by providing context to the spectra. Okay, I covered that pretty much. Now, you probably remember, maybe I mentioned in passing earlier that using different dispersing elements can give you benefits, but it may also give you drawbacks. For example, using diffraction gratings, you may get multiple orders of diffraction, and that was often considered a drawback for many applications, while it may have been a blessing for others. Nevertheless, here you see a schematic of a way to deal, well, to illustrate the problem. Here we not just have a diffraction grating, which is important to use. We cannot use a prism. We use a diffraction grating, as I repeat. The reason is that we need a very, very, very high dispersive power, which can only be successfully achieved, and in this particular wavelengths as well, in extreme ultraviolet light. That's the only way to do it. The multiple slits may give birth to multiple confusions of the spectrum coming from if those are 2 neighboring slits all plotted along the disk of the sun, and here is crossing basically the on-limb location, and here is actually outside in the atmosphere above the limb. One slit with a dispersing element may introduce different spectral lines at these fixed locations along the detector, basically our CCD camera capturing the spectrum. And the similar dispersion will happen at the other, coming from another slit. And as you see, there will be kind of a confusion. So the other slit produces, for example, a lower intensity in the spectral lines. So you see there will be locations along the grid of the detector that will have multiple orders of diffraction to different slits of the 37 slit array. Here you see a depiction of the different spectra within the spectral range. So the question is, can we overcome this kind of difficulty? Well, one has to solve a mathematical problem, basically an inverse problem, by inverting an array containing the velocity, the differential emission measure, and the slit positions. And you don't have to get into the details of that. It's a mathematical way of treating this problem by understanding the physics of it, that we always observe different columns of plasma from a different location in the slit and looking at the sky, and different velocities, of course, because we observe the spectra, and therefore maybe shifts of Dopplers and other effects. And we call this approach spectral disambiguation. So it's basically a minimization or optimization process using compressed sensing applications. You can read more in those publications underneath. This is already published and approved. And of course, we have to convince NASA, not just us and you here in this talk, that this should work. In our proposal to NASA, we showed in a convincing fashion that this problem is not just remediable in a mathematical sense, but can be done and proved using synthetic data from advanced 3-dimensional magnetohydrodynamic simulations of the solar atmosphere that produced eruptive events with the same time evolution that we see in the observations, and in particular for M-class flares. So here you see in all those pictures, you see scatter plots of the images produced by spectral disambiguation and the ground truth. And the scatter plots, as you see, the joint probability density functions are showing that we have pretty much a very, very good understanding and handling of how to go from confused spectral images to decomposed and corrected spectral images. So we know this will work. That's great. So very quickly, Muse constrains coronal plasma distributions, as I show here, with multiple diagnostics. One is a temperature, obviously through this inversion problem. One can extract the temperature, one can extract the Doppler velocity, one can extract turbulent and unresolved motions from the width and further processing. The spatial distribution of things, because we're going to have spatially resolved imaging, the temporal evolution, which is actually going to be very, very quick. As I said, almost 2 orders of magnitude faster than the existing instrumentation. And then, of course, allows to study the interdependencies and spatial consciousness. So you see this illustrated in this colorful plot here. Our instrumentation will obviously break current stalemate of competing models that up to now they are not testable by any of the current instrumentation. So we are very, very, very excited that NASA selected us. This instrument will also allow comparisons between different models on such small scales that make testable and distinguishing predictions, for example, about the nanoflare versus a wave heating of the solar atmosphere, one of the remaining unsolved, or one of those problems that have been solved many times, as some people joke, one of the unsolved problems in astrophysics. So it's needless to say, Muse will show us the sun in a very different, it's definitely a different picture of the sun that we already have. Muse's multi-slit approach will allow full spatial and simultaneous coverage of hot plasma in current sheets, flare loops, CMEs, as well as cool plasma in flare ribbons. And here you see a nice illustration here. Most of you that doing solar physics will probably recognize what this region is. It was observed, obviously, with AIA, but this is just a composite illustration to show what we expect to see with and what kind of coverage we expect. The contact would have this kind of field of view. You can see this kind of view. Actually, it can get double. It's all dependent on the telemetry rate that we'll be using. So this can be up to this kind of size, like stacking two of such field of views together. And there will be a smaller field of view, about 170 to 170 arc seconds at 0.4 arc second resolution, which is about, as we see in comparison to this feature here, that's about how big it gets, which is very, very, it's big enough to contain large active regions. And that's what we care about for most of this kind of science. And obviously a large chunks of the quiet sun all over the place. That is also important for our science. There will be spatial observing modes, which will allow detailed studies of flares and at cadences faster than 1 second. The context imager will provide observations spanning, as I said, this kind of large field of view at about 4-second cadence. So we're talking about something much faster, even though it's partial field of view, not as big to contain the entire solar disk, but essentially you get a very large portion of it at any given time with a wealth, an overflow of diagnostics, so to speak, and the physical ability to probe the physical conditions of the atmosphere and the sun. So Muse captures the full spatiotemporal evolution of UV line intensities, velocities, and broadening up to 2 orders of magnitude the cadence of existing UV spectrographs with an innovative multi-slit design. Will provide us with all different kinds of quantities. This is from a synthetic simulation or synthesized observables that you see here at different wavelengths from our 2019 work. And we used this to actually show during the eruption of the benefits of doing multi-slit imaging spectroscopy by leveraging the fact that we have multiple slits. So here is a typical way of making a raster. If you remember, I mentioned that you scan from left to right. Of course, you can scan in other directions as well if you roll the spacecraft, but you are able to form images that obviously have to develop in terms of time. So here you see how the time changes from time 0. So we're talking about several tens of seconds to make this kind of image of the simulation we just saw earlier. And here you see the Doppler information, something that we do not currently have. And that will be how UVST will be able to deal with this kind of problem. Well, we're saying that this is not enough. With Muse, we'll be able to cover this because of having 37 slits arranged in such a large 170 arc second range. So we'll be able to cover from left, well, only having to cover from the slit of the from one position of the slit to the next, which is only for about 4.5 arc seconds instead of 170 arc seconds that or even less, as you see here. So it will allow us to probe the physical evolution of extremely rapid events and develop in order of a few seconds, and using this classical use of spectroscopy or making spectroheliograms, will not be able to capture the physics. And here, for comparison from the simulation, that's an instantaneous snapshot of the simulation in for all of its glory, showing again the velocity. So you see the prominence that is erupting, and twisting motions or unwinding motions. You see red shifts and blue shifts. Blue shifts means towards the observer. You see plasma going towards the observer. Red means plasma going away from the observer. And you can see that how good of a job Muse will do in this kind of situation. Muse will constrain multiple initiation mechanisms of flares and CMEs. We're using such spectroscopic signatures that are often missed by single slit instruments, and will let us test different theories and models about solar eruptions, which involve different physical mechanisms. For example, bidirectional flows can show the reconnection trigger. And that's what we saw here. For example, this is a tether cutting evidence that you have reconnection happening higher in the corona, a few megameters above from the solar surface. This is a simulated limb view. And yeah, and obviously, what other wonderful things we can do, looking top down or from all different kind of angles of different events with our novel instrument. That's another way of viewing things. We have another simulation that we used. We synthesized the natural evolution using the full magnetocardinodynamic set of equations in 3 dimensions, including the effects of radiation. And we synthesized observables that will be observed by the spectral lines of Muse. So you see here the choice. We have iron 15, which corresponds to roughly to plasma of 2 million Kelvin. We have iron 21 corresponding to about 10 million Kelvin. So we cover both relatively cool or warm plasma and very hot plasma moments during the flare, leading to the formation of the CME. So a bit later, about 20 seconds before the eruption, you see a full-blown structure of a sigmoid, and actually you see the beginning of the motions. And this is actually the Doppler information. So that will actually serve as a way to test the hypothesis that we have pre-existing fluxes before the initiation. And that's really going to be groundbreaking because we don't really have such ways nowadays. And here is another movie using the same simulation that I showed you just before as static images, just to let you see what kind of high quality and physical modeling that we employ to constrain our instrument design. So very realistic for those who actually work on solar observations. They will recognize how such precursors of eruptions really appear in real observations. But here is the thing that they haven't seen, because we haven't seen with our instruments either, because that's not possible. And it's this image that you see right now, the Doppler information in those spectral lines at different temperatures, and probing essentially the evolution of the plasma flows at different heights on the solar atmosphere. And that's something we will be able to do at such high cadence. Okay, we covered that. Still keeping an eye to the time so that I will be fair to all of you for making the time and attending. I just want to say that for the past 2 decades, we have relied on coronagraph observations of Hel.A.S CMEs to estimate their physical properties. Muse will measure Doppler velocity maps of plasma erupting from the sun, providing important constraints to initialize the so-called data-driven CME models that will allow us to better constrain the prediction of space weather by understanding the initial conditions better. So we are very excited about that. Other fundamental topics, of course, is the so-called plasmoid instability, which is the prediction of fast reconnection models initiated by this kind of instability, and therefore explain the way we see dissipation of energy on the sun at various scales. So there are models already developed. There are theories, from analytical theories to MHD theories, and we have what it takes with our instrument to understand in views of the intensity of the Doppler shift and the line width, particular signatures that we expect if the plasmoid instability is happening on the sun. Essentially bidirectional flows, merging of plasmoids as as islands, plasmoid islands that are merging together with the characteristic signatures impact in the line width as well. So there are indications from AIA with features that people claim that they are plasma blobs, and obviously without having this spectral information and not being able to capture those rapidly developing features or phenomena or events, it's impossible to make conclusive firm conclusions. With Muse, we will be able to do so. Well, reconnection outflows in flare current sheets, that's another pressing issue to test the theory of modern theory of reconnection above our arcades. Basically, there is evidence on multiple termination shocks. There is a lot of controversy again. We will be able, with our resolving power of Doppler flows and intensities, to capture characteristic patterns that are predicted by models. So we are also excited about that, being able to solve that. We will also be able to elucidate the source of the nascent solar wind. And how is that? Open flux, which basically happens usually at the edges of active regions, is a source of the nascent solar wind, as we know. But we do not really have the rapid ability to probe the plasma. Muse rasters will be pretty much covering the entire region in, as you see here, in almost instantaneously, and actually double the field of view. This is just half in terms of the y direction. So you can imagine now about the characteristic size of active regions we can probe. And it will actually help us investigate the presence of waves and intermittency of perhaps from small reconnection events, maybe the braiding phenomenon or other mechanisms that originate in such areas. For example, you see here the width in kilometers per second, and also the Doppler flows that are blue shifts going towards the observer of 400 kilometers per second, roughly speaking, associated with locations where we expect to have the formation of the solar wind. Okay, I'm very close to the end of my presentation. We will be able to identify the heating mechanisms important for the sun's corona, basically, as we like to say, help solve or get closer at least, but we are confident we will help solve the coronal heating problem, because we have basically the ability to observe, test different theories, produce observables of different theories. And by doing statistics, observing multiple regions on the sun, we can test whether it's kink waves, regional absorption, or Kelvin instability dissipation. And given these observables, Muse will be able to observe such evidence in this kind of fashion, as we see. If there are torsion alpha waves driving this, we will actually see that evidence for turbulent dissipation, and the Doppler shift observables will appear like this. The intensity observables will appear like that in this choice of spectral lines here, for example. And the line width will appear here in this kind of coloring and quantities, intensities. And if we have Hel.A ice to do the same job, you see it will actually fail, because Hel.A ice, which is a current spectroscope, classical spectroscope, one single slit, it cannot really cover this at the particular speed or rapidity to capture, to allow us to do this kind of hypothesis test and distinguish between different competing theories. And not just competing theories, it may be possible that all of them actually happen to some extent, but at least we'll be able to measure things. Here, with the current spectroscopic abilities that we have in space, in current instruments, as you see, this is not possible. So not a surprise that the coronal heating problem has been solved many, many times. So probably some of the people in the audience remember this has happened, from the beginning of the career several times, as I just said, jokingly. Okay, just putting in perspective why Muse was selected. There has been the so-called next generation of solar physics mission panel of solar physics experts, was designated by NASA, ESA, and JAXA. So as you see, a very large collaborative effort that happened about a decade ago, and it resulted in the formation of several white papers and one major publication. We did listen to what the community essentially needed, and this is why we ended up with Muse. Obviously, for a coronal and transition laser spectrograph, we didn't really have to bother. That's a classical spectrograph, and solar C, or the so-called UVST, which is exactly the same, is now known UVST, is going to cover this space. Now, for chromospheric and photospheric magnetograph spectrographs, will rely obviously on DKIST, the very powerful 4-meter telescope in Hawaii, and other ground-based observatories all over the world. Some of you in the audience that I see are involved with the ground-based observatories. We are very, very eager to collaborate with you and expand the capabilities of your observatories and also of our own science investigation and propel the understanding of our field forward by this synergy. And here's where we sit. We sit between the spectrograph, classical spectrograph capabilities, and also coronal imaging capabilities, again in a sub-second resolution. And we are very excited. There are two papers that are summarizing the science behind what Muse will be able to do. So take my presentation as a very crude summary of this. And if you want to delve into details, just look for, this should be correct, this is 2022. Both of those papers were accepted in, I believe, February, earlier this year. So that's it from me. And if there are any questions, I will be very happy to answer.
Thank you very much, Yorgo, for the very nice talk. So now time for questions. So first of all, if somebody wants to ask a question, please raise your hand. But in the meantime, we got a couple of questions from Adele on the chat. So it's talking about essentially whether the small scale measurements can reveal anything about the physics of the temperature in the corona, and what are the main scientific questions regarding solar physics.
I believe I covered it in passing. I suppose,
yes.
Yeah, Bebe actually answered that. From what I see in the timestamps, he asked those questions before I went to those slides. So maybe I had a very long introduction, but I wanted to put things in perspective and build up build up the anticipation for that. So I hope that I addressed Bebe's question.
So other questions, comments, please raise your hand or speak up.
Hi, Yorgos. This is Lucas. How are you? I was really happy to hear you. It's an excellent talk. I wanted to concentrate my question on the multi-scale problem that we have. You speak a lot about the small scales, but what about the larger scale? I mean, I didn't catch very well what instruments you have and how you will be covered observationally from the large scales.
Yes, here is probably the proper slide to actually address the large scales. Here you see basically the context imager being able to measure this area, this space on the solar disk or covering the atmosphere as well. And that's only half of it. We can actually do double of that and basically form a kind of a rectangle, if you like. Our instrument is a partial field of view instrument. It's not able to do all this kind of wonderful measurements in the entire field of view that is needed to cover the entire sun. So we have to draw the line somewhere and actually live with a compromise. And this is actually having a limited field of view instrument. But again, the size of the instrument is actually, the field of view is selected to be such that will allow to fit inside large regions containing active regions, which essentially are the large scales that Lucas, I think, is pointing to, looking at the dynamic evolution of such regions, and essentially the initiation of solar eruptions and sea structures extending, for example, if they are on the limb, several megameters away from the surface, or if we are looking top down, still being able to capture such regions with lots of legroom, so to speak. Now, for the spectroscopic capabilities, we have a narrower field of view, which is about 170 to 170 arc seconds. This is roughly about 1/3 of this field of view along the X direction, and about half along the Y direction. So as you see in this inset images here, this covers the region where such macroscopic structures, for example, post-flare loops, can fit very, very well. And this is actually a very big set of post-flare loops. Normally, they're actually much smaller from most active regions. And nevertheless, in my last slide, which is really tough right now with all the graphics that I have, I can show you that we can also fit successfully large active regions within our field of view. Or, for example, you can see here, this is the field of view showing an actual active region. It's simulated view, but it actually shows how this will fit. And this is, again, half of the field of view. So I think that hopefully addresses your concern, Lucas, on whether we have the ability to look at large scales, not just the small scales, but also large scales with the same capabilities that we have about diagnostics and physical information to understand the small scales. We are very, very confident and very, very excited to see this mission being developed as we speak, and actually get to the point to get the data and perform these hypothesis tests.
In your language, the small scales is what is the minimum distance or the minimum length that you have in mind, where you actually wanted to report current sheets and things like that.
Yes.
What exactly is the minimum of the size that you are going to be recovering?
Okay, that's a very good question. For the minimum scales, obviously we have the limitation that has to do with the pixel resolution, if you like. So if you want to do spatially resolved studies or spatially resolved features, but using the spectral diagnostics, for example, as you see here, we have the Doppler shift and also the line width. In particular, the line width can tell us a lot about unresolved structures smaller than the ability to resolve them, especially with our pixel. So the width is holding information about turbulence, for example, that I know you're very, very interested in, MHD turbulence. So we'll be able to actually probe structures that are not necessarily resolved by eye with our instrument, but they are hidden within the realm of the scales that are not possible to be resolved even with scaling up our instrument. So we cover the space because of the type of diagnostics we will be providing, and that is not just the intensity across the spatial dimension, but also Doppler shifts and actually line widths. So I hope that also addresses the question about.
That's fantastic. Thank you very much, Giorgos. Excellent, excellent. Thank you very much.
Thank you.
Thank you. Other questions, comments? Please speak up.
Yes, Spiro. Can I make a question, please?
Yes, of course.
Yeah, so it's a very exciting news, Giorgos. Can I ask you something? What about the technical question about the calibration of the Doppler shifts? I think that in these spectral ranges, we don't have, usually we use chromospheric lines to calibrate the wavelengths. Do you have any new methods or something about, have you thought about this problem?
Of course, yeah, that's actually a very, very good question. Obviously, we'll have a large field of view that we will be able at all times to observe, for example, an active region structure within regions of quiet sun. So we will be able to actually get relative centroiding looking at a particular region on the sun. The other thing is obviously that Muse cannot really do all this hard work without having input from models. So we also have, this is the same case with IRIS. IRIS was a mission having exactly the same philosophy in its development. A lot of the physics of the lines that we use and a lot of the physics that are needed to understand how well we can constrain, for example, measurements like Doppler shifts, have been based on numerical simulations, cutting edge numerical simulations. So in similar ways, Muse will obtain and achieve such ability to do centroiding and calibrate the Doppler shifts by not only by the ability to observe large areas, much larger than IRIS, for example, in that regard, and with different spectral regions and diagnostics at the same time, but also being informed by cutting-edge models that will allow us to fine-tune the particularities of the calibration. So it's a joint effort. It's both theoretical and observational. So our investigation has also requested and have secured funding from NASA to develop such ways to address the issue of the calibration. That's an excellent question, by the way.
Thank you. Can I make another one? I have just about the detector. You know, detectors of such instruments can be very worrying. For example, Sumer had an excellent detector for low intensities, but was saturated for higher ones. And in IRIS, we had very interesting spectral lines that were very, very faint. So have you what's going on now with this instrument? Would also cases with very faint lines where it could not get ridden from the noise, for example?
I see your question. Let me show you here. Here is actually the collection of the lines. Now we use Chianti, of course, as a way to synthesize the particular spectrum within our passband, the way we decided to optimize the way the instrument will work. And so the dotted line shows the passband, which suppresses the spectrum outside of its extent, and inside you see the dominant lines. Obviously, we have multiple lines, and we don't really care about the small lines. We have done an extensive work based on our criticism by NASA, so we actually successfully addressed it. That's why we were selected in showing that if we have any faint lines or any other lines that are possible contaminants, we'll be able to extract them in a very in a successful way. Or if there is any contamination, that will be very close to the noise level. So we were able to demonstrate that. Now, the lines that we are particularly interested, obviously, are not the faint lines. They are the strong lines. And this is what drove the particular choice of lines in the sense of having a particular setup in our instrument to accommodate such particular passbands. We are interested in the 171 channel, for example, because of the particular iron line and transition region. We're interested in the 284, which is about 2 million Kelvin formation, temperature formation for that line. And we're also interested in the 108 angstrom channel, which is actually giving us the opportunity to observe contribution from 10 million Kelvin to 12 million Kelvin with the lines that are there. And that's actually for the spectroscope, the spectrograph, the imaging spectrograph, the multi-slit imaging spectrograph. For the context imager, we have a 304, which is obviously a transition region, about 50 kilokelvin, and 193, which is about about 1.5 million Kelvin, and perhaps with some contribution from flaring, what can get you all the way up to 10 or more, maybe 20 million Kelvin. So we have a very good coverage in terms of the lines we really want to observe, and this allows us to be not just confident, but also demonstrate with modeling that this will not be an issue in the way we understand the spectrum and the way we will do the science. So hopefully that addresses your concern and your question.
Yeah, thank you very much.
Okay. Mm-hmm. There is a question from Vishal in the chat. Do you also expect the line widths to be as correctly disambiguated as the Doppler shifts using the compressed sensing method, especially since the community would want to study non-thermal widths, for example?
That's a very good question. Obviously, we as an investigation, as much as the community, are interested to do a good job in characterizing the non-thermal widths. That's why this is a major part of our proposal to NASA, the ability to actually disentangle the width information from the spectrum. And indeed, having done all this modeling, and this was a major part of our effort to show conclusive evidence, it shows that we are able to have a very, essentially recover the ground truth by doing as much of a good job as we can in synthesizing the characteristic atomic physics and the characteristic plasma conditions using cutting edge 3D image simulations. As you see in this plot, this is also available, I believe, in one of the publications. I think is the Depontiu et al. 2022, where we show these figures here, so one can actually go and see for themselves. So we are very confident, based on our understanding of the instrument and the specifications that we chose, the very carefully chosen particular specifications for the instrument design, that the thermal width will be a very, very valuable quantity to play with and do discoveries with. Yeah.
Okay, we have a question from Tassos. So Tassos, please go ahead.
Hi, George. This is very nice. Thank you for this very interesting and enlightening talk.
Sure, thank you.
Can you go back to the I'm following this line of questioning now. Can you? Mm-hmm. Yeah, here. Yes. You said here that this is a no. Go to the formulas.
Here.
No, in the inversion where you have the velocity differential emission measure.
Yeah.
Okay.
Okay. So if you said okay, this in reality it's an inverse problem.
Correct.
Yeah. Okay, so most of this kind of problems are ill-posed problems, as we know.
Indeed.
And in this solving these problems, you have a solution that it's given you a family of solutions, and you have to find out which is the right one. So either you have to use a single value decomposition process, or you have to go and make some kind of a validation. So how are you gonna do that? How are you gonna do that? That's my basic questions, and this is the basic questions to all the instruments that they are using this kind of inverse problem solutions.
Trust me, we received this question from the NASA panel, so we are very well.
I'm sure that you have received it, but
yes,
how are you really gonna do it?
The answer is that we are doing it. The answer is we are doing it, and the way we do it is actually depicted here, illustrated or summarized in this slide. And I invite you, because there is not enough time for me to actually go through the details.
Okay.
I invite you to go through these papers, 2019, Chung et al., which in particular, this paper is probably responding to your question, how this is even possible. And we actually show with our essentially line of work and our sophisticated image simulations and having the so-called hare and hound approach, having a validation of the methodology.
Okay, so you use the hound approach.
Say it again.
So you use the hound approach.
That's essentially what we're saying, yes. And that's basically what you see here. Here you see the ground truth and the inverted truth, so to speak. And what you see here is the joint probability density function. And we have essentially done very careful characterization of the inverse problem, its space of validity, and how much we should expect from it. And what we've shown, much to our pleasant surprise, is that this method works. So there will be times that this would scale, for example, with how much width in the Doppler shifts that happen there will have, because that will actually increase the so-called spectral confusion. So if you see here in the dispersive element, you have a set of spectral lines, essentially the strong peaks. Actually, you see 3 strong peaks and 3 wimpy peaks. So if the wimpy peaks, the lower intensity peaks, are actually more modified because there is a lot of Doppler shifts there along the line of sight, along the column, then things will actually be either more broadened or even more distorted along every spatial pixel, which means at particular locations there will be more challenges than ease to solve this inverse problem. But what we actually shown in a statistical fashion, having a range of different intensities. Here I only show one, for example, but as you see here, we have Doppler shifts of order 300, which is basically close to our free spectral range. So we know that from what we can measure, and for the majority of the cases that are observed on the sun with currently known techniques, for example, other spectroscopes, we know that we should expect such particular values happening, for example, in quiet sun conditions or in active region conditions. So we know what to expect pretty much, and therefore we have a way to do it on a point-to-point or pixel-to-pixel validation across a large range of values and parameter space to show that this spectral disambiguation code or method works successfully. So yes, indeed, that was a major part of our narrative, a major part of NASA's criticism on whether this measure will succeed. And from what it appears, we actually not just succeeded to convince ourselves that we can do it, but we managed to convince NASA and the panel of experts that this is actually achievable.
Okay, George, thank you. I'll go through the publication you're referring to.
Of course.
Okay, good. Thank you.
Thank you. Other questions, comments? Yannis, please go ahead.
Thank you. Thanks, Yorgo, for this great demonstration of Muse. Actually, yeah, I think we were all happy hearing the news. So maybe it's a mundane question, but I would like to ask, what's the data policy and if there are any plans, specific plans for coordinated observations. And the final part of the question has to do with how long will the pipeline be able to produce the data products after the observation?
That's a very good set of questions. Indeed, let me show you the final slide. Sorry, with those graphics. I try to be theatrical here with my slides. Now paying the price. If I go to my last slide, I will show you the level of synergy we expect. That was a major, here is the last slide. That was a major driver behind the way we pitched our product to NASA, so to speak. So we do want to have a synergy with ground-based observatories. There is no way really to address many of those important problems without this kind of synergy. So you see on the very right, we expect to have a certain amount of overlapping observations with DKIST and also multiple other ground-based observatories, both in the US and abroad, definitely in Europe, and definitely with some of the observatories that you're involved with. So that's really our goal. For example, that's the way to get magnetic field information. We do not really expect HMI or MDI, for example, to be continually available to us. So at some point, it may be possible that NASA will pull the plug. We're going to end up without a magnetograph in space. So what will be our way of carrying out or getting context about the magnetic fields? Well, guess what? Through ground-based observatories. And beyond that, we cannot really put everything into a shoebox and fly it to space and call it a magnetograph, right? There are certain things that can be done only from ground. And not just about magnetic fields, but also by expanding the diagnostic capabilities that we have collectively. And indeed, the synergy is essential. So that's what we expect. The other part of your question about when the data, how long it will take for data to be processed. Well, a major part, again, of our proposal was to actually get funds to scale up our disambiguation code and computing capabilities. So in our data center, essentially, that will make the data available to the public in a way that it will make the data available at a regular pace. Pretty much the way you see it happening with HMI and AIA investigation. The key thing here is that while we have inverse problems to solve, but actually a smaller size of the image, so it's going to be 1K by 1K, for example, right? Because it's a 170 arc seconds by 170 arc seconds. So it's actually smaller than doing this for a 4K by 4K image, but again, a very high resolution given the spectral the spatial size of the pixel. So the answer is that it's not impossible. We have numbers in hand, and we know this can actually happen in a real-time kind of fashion. So that hopefully addresses the question of how quickly the data will be processed. And the last part of your question, when the data will become publicly available, we are very proud on the way that we've been running solar missions since essentially the beginning of since the SOHO time. Lockheed had an active involvement in producing MDI. It's managed by Stanford, but was built by our own team here at Lockheed. And the team of co-investigators and the PI at that time have had a major drive in pushing for advocating for open data policy. Up to that time, solar physics missions were up to the mercy of the PI. Does the PI want to give the data to somebody? Then that somebody will get the data. If the PI wants to embargo the data, they were keeping it for themselves. Pretty much the same way it happens even nowadays for the ground-based or spaceborne nighttime astronomy. Everything is actually at the mercy of the PI. We are very, very proud, I repeat, that our lab since the 90s has actually started this open data policy. So as soon as the data are actually down to the ground and they are processed, they are becoming immediately available to the public for everybody in the global community to make use of and make discoveries from.
Okay, that's really great to hear. Thank you. So I understand that data will be prepared in timescales closer to other space missions than to ground-based observatories, right? It will definitely not take months or
absolutely not. Yeah, exactly.
Yeah.
Exactly.
Yeah.
Real time. Think of it as real time.
Thank you. Other questions, comments? Okay, I got two short questions. So first of all, how are you getting involved with Muse? What specific tasks you have to deal with this mission?
Well, I'm basically a senior scientist here at Lockheed, and my duties actually are to build the instrument. So I've been involved in multiple different ways over the preparation of this proposal. I have been actively involved in presenting parts of some aspects of the proposal in the NASA team of experts. I also helped address essentially criticism by NASA regarding the science. So I had this scientist involvement in this whole effort. And then my current effort is actually, as we speak right now, is to help build this instrument. Since now this is all agreed and approved by NASA in terms of science. We scored excellent in terms of the scientific merit, and excellent also in terms of the proposed instrumentation. At the end, we got the best grades possible. But what we want to do is to ensure that this will happen within the timeline agreed with NASA. So my duties will be to basically help on setting the test bed and on using ground support instruments essentially, and perform tests on optical benches and characterize the throughput of the instrument, and that will not just be done through lab work but also through modeling work. So characterizing the instrument response to the theoretical level. So have basically the initial design and see how we can even make it better than what we proposed. So all those things are still fluid in the sense of they're being revised. And this is the effort of, not just meeting our specifications, but actually make it even better. So I will be involved in all those aspects. And eventually I will also be happy to see this thing fly. So as you see, I will be a major investment of my time as a scientist here at Lockheed to build this instrument and actually see it fly.
Okay. It seems you'll be very busy with all this. So my second question is about the data. So basically the backbone of the whole data analysis is the inversion of the data. So my question is that, as I understand, you will supply, the inversions to the community, but is it possible also for somebody from the community to perform his or her own inversion of the data, or is it kind of, you need a supercomputer or things like that to do this?
You don't need a supercomputer. And obviously by the time you get the data, when we fly the mission in 2026, if Moore's law is still valid, you will be able to do things that you cannot imagine with your current computer. One thing is this, of course, that's a joke, right? But the point is that obviously everybody will be able to use, different levels of data, similarly as done, with other space missions, level 0 data, right? So that's really what it is. But our goal as a team, as an instrument team, will be to ensure that you get the data to do the science in the best way possible. Obviously, we'll trust more the instrument team about, doing the proper calibration of the data than, I suppose, experimenting with different parameters and see what you can get on your own. We've seen that many times, and also in my experience, I've seen that many times in my own experience as a scientist, that I made more progress when I had kept the instrument team of a particular instrument involved or know what I'm doing than just doing things on my own, because the instrument scientists know exactly what gets into the calibration process. They will know exactly whether this is trustworthy or if this is a good way to analyze the data, or if this is not a good way to analyze the data, for example, given a particular limitation of the scope or the scope of the data. So my advice is to, first of all, the answer is yes, you will be able to do it on your own, obviously. But I urge the community to always keep in mind that, the instrument team is actively working on making the data as perfectly calibrated as possible. So that probably answers the question.
Okay, thank you. Other questions, comments? doesn't seem the case. So let's thank again Yorgos for the very informative seminar and everybody for tuning in. So have a nice evening, everybody.
Thank you.